These are notes for 1.1, properties of real numbers. Okay, so we're just going to go through some properties first, and then we will go into how we break down real numbers, the different categories. All right, so it says the additive blank of any number a is negative a. So if I gave you 2 and negative 2, the general word we like to use, opposites. So over here we'll just put opposites. Right, 5, negative 5, those are opposites of each other. Okay, but the actual property is called the additive inverse. Okay, so the additive inverse of any number a is negative a. So those are opposites. So whenever we're talking about an inverse, we're really just talking about opposites. Okay, and then the sum of opposites, 2 plus negative 2, 5 plus negative 5, negative 12 plus 12, all of those opposites will always give me 0. Okay, 0 is also important when it comes to additive properties. So 0 is actually known as our additive identity. Okay, so 0 is our additive identity. So the way I remember the difference between an inverse and an identity, I go inverse is the opposite, and identity is something that could be added that's not going to change the number. An identity is going to keep the number the same. So that's why for addition, it's 0. 2 plus 0 is 2. 12 plus 0 is 12. So on and so forth. So that is why it is our additive identity. Okay, so those are like our additive properties. Now we're going to talk about our multiplicative properties. So the multiplicative inverse of any non-zero number a is 1 over a. Hopefully you guys remember what this relationship is called. So if I had 3 and a third, if I had 2/5 and 5/2, if I had negative 12 and negative 1/12, those are called reciprocals. Or another word, opposites. Those are opposites of each other. They're reciprocals of each other. So again, when I talk about inverses, we're talking about opposites. So the additive opposites would be like positive and negative, versus the multiplicative inverses, or the multiplicative opposites, are reciprocals of each other. Okay, so whenever I multiply together 3 and a third, 2 and a half, whenever I multiply together reciprocals, I'm always going to get 1. Let's go ahead and highlight 1 so we don't lose that. Okay, so we're going to go ahead and get 1, and 1 is going to be our multiplicative identity. All right, so just like our additive identity, which was 0, it didn't change my number. Same idea, the multiplicative identity, I can multiply by and it doesn't change my number. So 7 times 1 is still 7. My number stays the same, so that is why it is the identity. The last one we're going to talk about here is the blank of a real number is the distance. Keyword distance. Let's go ahead and highlight that. The distance from 0. You guys, hopefully in your heads, are answering this. Whenever we talk about a distance from 0, we're talking about its absolute value. Okay, some of us were just told the absolute value is just positive without understanding why it's positive. So the reason it is always positive is because it's a distance, and it's impossible to go a negative distance. Even if I drove my car in reverse, I'm still going a positive distance. So absolute value is a distance from 0, and that is why it is always positive. All right, let's go ahead and scroll down. So if you guys notice on my chart, I went ahead and drew a bigger box around this whole graphic organizer. I would like you guys to do so right now. So you're going to draw a big box around this. And then in that box, like I did, I put real. So the big category that we're talking about here is real numbers. And if you need to, just pause the video and get caught up. So everything we're doing so far and at the beginning of the school year, we're only dealing with real numbers. If a number is not real, then it's imaginary. And if it's imaginary, you know it's imaginary because it will have this like little kind of like cursive I or italicized I next to it, and that's how you know it's imaginary. If it doesn't have an I, it's real. Okay, so pretty much everything is real unless it has that I. So when I test kids on this every single year, like on my tests or whatever, I've gone, okay, tell me all the things that this number is. So maybe I give you 2, and you have to tell me everything that 2 is. Most kids forget that it's real. So everything is real. Please don't forget that these are real. All right, so from real, this graphic organizer kind of goes backwards. So we're going to start at the bottom, work our way up. So from real, the number is either rational or irrational, okay? In simple terms, if it can be written as a fraction, it's rational. If it cannot be written as a fraction, it is irrational. So I'll go ahead and talk about rational ones first, just because they're a little bit easier to understand, and then we'll talk about what could be irrational. So, for instance, like the number 2 is rational. The reason it's rational is I can write this as a fraction. So if you guys wanted to, 2 is technically over 1. So 2 is rational. I write it as a fraction. Easy enough. Okay, let's do another one. What about 1/2? Can 1/2 be written as a fraction? Well, yeah, it's already a fraction. What about 3.14 without the decimal continuing? This is rational as well because I could put this over the place value. So this is the 10th spot and then the 100th spot. So I could write this as 314 over 100, and now it's a fraction. 1.35 repeating. Whenever something starts repeating, it was a fraction at some point. So whenever it's repeating, and it repeats, like for instance, like 1/3 is point, what is that, 3? Yeah, point 3, repeating forever and ever and ever. No, that's, yeah. Okay, so that's the idea behind the repeating. So the repeating was once a fraction. We could have like mixed numbers like 2.5. Yep, good to go. Okay, so those are all rationals. Rationals can be written as a fraction. Rationals can be written as a fraction, so on and so forth. Okay, now let's talk about irrational. Irrational cannot be written as a fraction. Cannot. Okay, so one that we all should know, is pi. Pi is 3.1415, blah, 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 right? So that decimal never, ever, ever ends. So since it never ends, I can never write that as a fraction, okay? And like I just said, repeating decimals. So maybe we have like, I don't know, 2.7953 dot, dot, dot. That dot, dot, dot tells me right there that I cannot write that as a fraction because that's going to continue forever and ever and ever. All right, some other ones that we could see. Square root of 2. Square root of 2 is going to give you a decimal that's going to repeat forever and ever and ever. Square root of 3 would do the same. So these are irrational. Another one you guys probably haven't learned about yet, but we will talk about it a little bit in this class, is E. E is the same idea as pi. So E comes into play with like statistics or like compound interest, things like that. So E was like this repeating number that we kept seeing over and over and over, especially in interest. So they just gave it the letter E, and your calculator has a button E, just like pi. It's the exact same idea as pi. All right, so Step one, everything's real. Step two, you're going to ask yourself, is it real or irrational? Or not real, sorry. Rational or irrational? Rational can be written as a fraction. Irrational cannot. All right, if it is irrational, it can't be anything else. It's just real and irrational. If it is rational, we could go even further and see, is it an integer? Okay, so next we're going to talk about integers. So integers is the number line. So those include negatives and those include positives. There will not be decimals or any fractions. So our integers go, we'll go dot, 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 -3, -2, -1, oops, -1, 0, 1, 2, 3, dot, dot, dot. Okay, so those are our integers. So next we ask, okay, is it an integer? Yes, or maybe it's not. Like 1/2, not an integer. So if we were looking at 1/2, it would only be real and rational. If we were looking at -5, -5 would be real, rational, and an integer. And then the next more specific one we could get is whole numbers. Okay, so whole numbers and natural numbers are actually really similar. Whole numbers includes one number that natural numbers does not. Whole numbers includes 0 and then all of the positive integers. So this is 0, 1, 2, 3, 4, dot, dot, dot. Okay, so if we were asking ourselves about 0, 0 would be real, it would be rational, it would be an integer, and then it would be a whole number. 0, however, is not a natural number. So how I remember the difference between whole and natural is if I went out into the natural world, right, like, I don't know, I'm in the middle of the desert or something, I'm not going to start counting cactuses with 0. You start counting with 1. I go, oh, there's 1, there's 2, there's 3. So those are natural numbers, something that naturally occurs in the world, pretty much. Where whole numbers, like 0 was created as a placeholder, so like 0 is kind of man-made, and natural numbers is not. So this starts with 1, goes to 2, 3, 4, dot, dot, dot. All right, so what I like to do is I like to ask, okay, I'll give you a number or whatever the case is, and you would have to tell me what they belong to. So you always start at the bottom with real, and then you're gonna go rational or irrational, and then if it's rational, that's when you ask yourselves integers, whole numbers, natural numbers. So for instance, if I gave you square root of 5, square root of 5 is gonna give you a repeating decimal, so it's real, and then it's irrational. And then if it's irrational, there's nothing more to check. Like that's it, it's just irrational. Okay, if I give you 12, like 12 would be real, rational, an integer, a whole number, and a natural number. If I gave you -1/2, that would only be real and rational. It would not be an integer because integers are whole numbers, negative and positive whole numbers. All right. So hopefully all of that made sense, and we're going to go ahead, flip the page and go to the next page. All right, so now we're going to talk about the subsets. I literally just explained all of these, so hopefully you guys got them down. So let's start with the first one. These are numbers used for counting. So again, I walk outside and I start counting. When I start counting something, I start counting with 1. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these ones are called natural. Next one, they're natural numbers and include 0. Keyword includes 0. So when it includes my 0, let me change back. Give me a second, my pen is not changing. There we go. So if it includes 0 in their naturals, those are called whole numbers. Okay, next one is natural numbers, their opposites, and zero. In other words, this is the number line. So the number line is integers. Okay, next one can be written as a quotient of integers. In other words, quotient of integers means fraction. So when something can be written as a fraction, then that is rational. And then if it cannot be written as a fraction, this is irrational. All right, so hopefully you guys understand all of those. Let's go ahead and move on down. All right, classifying a variable. So it says your school is sponsoring a charity race and participants make a donation D of $15.50. Which set of numbers best describes each of the following? Okay, so the number of participants in the race. So it wants the most specific subset of real number that I can possibly write. So the number of participants. First off, we know that has to be a whole number because we can't have half of a human, okay? Now the question is it a whole number or is it a natural number? We know it's not integer because there can't be negative people. But can there be 0 participants in the race? And I would say, yeah, nobody enters the race, so there's 0 people. So this would be whole numbers because what if no one enters? All right, so the donation for the participant. So we're talking about 1550. What is the most specific subset of 1550? Well, it's real, obviously. Next, is it rational or irrational? This is rational because I can write that as a fraction, 15 and 1/2. And then the next question is it then an integer? So an integer does not have decimals. Well, no, it's not an integer because there's decimals. So the most specific I can get on this is rational. All right, the total amount of money raised. Well, it could go one or two ways. So if there was an even amount of people that entered, then it would be a whole number, right? Because 50 cents and 50 cents gives me a whole dollar, there would be no decimals. But we don't know how many people are entering the race. So it could be even or odd. So the most specific thing I could say is that this is rational because we don't know if there's going to be 50 cents at the end or not. And then the average running time of the participants, well, if you've ever ran in a race, it's like, took you 2 hours and 58 seconds or I guess I skipped minutes. It took you 2 hours and 12 minutes and 58 seconds. So again, the most specific, that's not going to be a whole number. It's not going to be on the dot that everyone ran exactly 2 minutes. Everyone ran exactly 5 minutes. It's going to be some sort of decimal. So again, the most specific I can get is rational. All right. Next, I mean, really this right here is like going back to elementary school. Hopefully you guys can graph all these on the line. So what I want you to go ahead and do is pause the video right here. Go ahead and plot all of these on the number line and then play the video so then you can see if you got it right and compare it with mine. All right, so this one, square root of 5. So I know the square root of 5 is bigger than the square root of 4. So the square root of 4 is 2, so this is going to be 2 and some change. So somewhere in there, it doesn't have to be exact. Okay, negative 1.4 repeating. So this is going to be smaller than negative 1, so it's going to be past negative 1 by 0.4. So from here to here is negative 1, and then this is about 0.4 past that. So this is negative 1.4 repeating. And 1/3 is smaller than 1. It's a third. past 0, so that would be my 1/3. Next one, square root of 17. Well, we know the square root of 16 is 4, so this is going to be like 4 and some change. So somewhere in here. Negative 4.6, so we have to go to negative 4, and then we have to go 0.6 past negative 4. So that would look like somewhere right there. And then 2 and 1/4, so I go to 2 and then a 4th past 2, and that's 2 and 1/4. All right, last one, absolute value. We want to graph the absolute value of negative 4, so that's going to be 4. Okay, 12/5, so 12/5. 5 goes into 12 twice with a remainder of 2/5, so this is 2 and 2/5. So 2 and 2/5 would be like somewhere right there. And negative pi, so that's negative 3.14. So we're going to go to negative 3 and then go 0.14 past, and that would be my negative pi. All right, next page. Okay, now we're going to go ahead and compare these real numbers to each other. Just make sure that you're just paying attention and not going too fast, because sometimes when we get to the negatives, we confuse our signs. So let's just be careful. All right, square root of 26. I can guesstimate square root of 26 because I know the square root of 25 is 5, and this is just going to be like a tiny bit past it. So this is just an estimation, like this would be like 5.1. Okay, so now we can compare these two. Well, obviously 5.1 is less than 6.25. Next one, the difference here is 0.22 or 0.23. So which one is smaller? Is 0.22 smaller or 0.23 smaller? So we can see that 0.22 is smaller than 0.23, just by a tiny bit. Next one, the square root of 4/9. Hopefully you guys recognize, I know the square root of 4 and I know the square root of 9. So the square root of 4 is 2, the square root of 9 is 3, so I'm really talking about 2/3. And hopefully you guys know that 1/3 is 0.3 repeating, so 2/3 would be 0.6 repeating. So these are actually equal to each other. Next one. Okay, this is the one I really like, and you should pay attention. Let's star it. Okay, so if you guys pay attention, the square root, okay, we have to think about this. The square root of 0.09 and then the square root of 0.1. So if we're ignoring the negatives, let's ignore the negatives. I can tell, or I know that the square root of 0.09 is technically smaller than the square root of 0.1. Okay, it's going to be smaller because 0.09 is a tiny bit smaller than 0.1. Here's where it gets a little bit confusing. We're talking about this in the negative sense. Okay, so really when it's negative a smaller number, so for instance, like let's pretend like this is negative 3 and this would be like negative 4. Well, negative 3 is actually greater than negative 4. Same idea. This one's going to be a little bit smaller, but when it's in the negative sense, it's actually bigger. So hopefully that makes sense. So again, like another example, like this would be like negative 3 to negative 4. Negative 3 is actually bigger because if you owe someone $3 versus $4, you're in less debt with $3. All right, and then the next one, pi is 3.1415 ... So since this one continues forever, that one's going to be bigger than the one that stopped. Last one says, let A, B, and C be real numbers such that A is less than B and B is less than C. How do you compare A to C? Explain. Hopefully you guys remember this from geometry. You guys did this like 5 million times. So I'll draw a little visual here. So let's just pretend here is 0, and we'll call this as A. And we know A is smaller than B. So this is B. So A would be less than B. But B is going to be less than C. So now we're asking ourselves, how do I compare A to C? So then how is A compared to C? And as we can see, A is going to be less than C. I'll be surprised if you guys remember this property, but like I said, you guys did this a lot of times in geometry. This property is called the transitive property. So transitive property is if A equals B and B equals C, then A equals C. We did that a lot in proofs in geometry. All right, scroll it on down. All right, we're going to talk about some more properties of real numbers. So again, our properties could be additive properties or multiplicative properties. So that is why we have two columns. It's an additive property, multiplicative property. So the first one is called the closure property. I don't really test on this one, but we will write it down. So A, B, and C are all real numbers. So we're assuming everything is real, nothing's imaginary. So if I did A plus B, if I add them together, it's going to be real. So this is a real number. Same idea with multiplication. A times B would be a real number. Oops. So hopefully this makes sense to you. If I have two real numbers and I add them together, it's going to give me a real answer. Like there's no way it's going to give you imaginary because they're real. So if I add two reals together, it's real. If I multiply two reals together, it's real. Okay, commutative. So the way I remember commutative is commuting. And when you commute to work, commute to school, whatever you commute to, you're moving. So that's how I remember this. Commutative, I'm moving. So commutative says A plus B is equal to B plus A. They moved positions. Works with multiplication. A times B is equal to B times A. And we know that. 5 plus 2 and 2 plus 5, same thing. 5 times 2 and 2 times 5, same thing. Okay, so commutative, they moved positions. Associative, I remember who my associates are, or like my group of friends. So grouping changes. So your grouping is going to change. So the order remains the same, just the grouping changes. So I'll show you. So this would be like A plus B plus C equals A plus B plus C. So associative is your grouping. So if I put A plus B in parentheses, will be the same as if I put the parentheses around the B plus C. Okay, so the grouping changed, my associates, my group of friends. Grouping changes, order remains the same. Same thing with multiplication. I would do A times B times C is the same thing as A times B times C in parentheses over here. All right, identity or additive identity. So again, the identity is something that does not change your number. So what can I add to a number and my number remains the same? 0. So the additive identity is 0. Okay, what do I multiply by and my number stays the same? 1. So the multiplicative identity is 1. A times 1 equals A. Inverse, opposite, opposite. So if I had A, the opposite would be negative A. Equals, and it will equal your identity, 0. Okay, for multiplication, it's going to be your reciprocal. So it'd be A times 1 over A, which will equal my identity, which is 1. And then our distributive property here. distributive would be A times B plus C. We need to distribute to everything inside of the parentheses. So I'd get A times B plus A times C. And we're actually going to add one more little one right underneath here. The last one is called your zero property. And the zero property says anything times 0 equals 0. Perfect. Okay, so we're going to go ahead and look at these and say what properties are illustrated. Okay, so the first thing I'm going to check here is, did the order change? Well, looking at this, it goes -3, 5, -2, -3, 5, -2. So it's not commutative because commutative switches spots. What did change is the way that they're grouped together. So my group of friends, my associates. So this is the associative property of, and then this is using addition, so it's associative property of addition. So associative property of addition. Look at my next one. So you guys can, hopefully you guys see what happened here. I have 3 times G plus H plus 2G, which is equal to 3G plus 3H plus 2G. So if you guys notice, I went ahead and distributed that 3 to the G and to the H. So this is distributive. Okay, and then this one may be a little bit hard to identify right off the bat, but it says 6 times 1 minus 2 is equal to 6 minus 2. So this 1 right here, so that's what we're really looking at. That's what changed. We multiplied by 1. Well, why are we able to multiply by 1 and it remains the same? That would be because of the multiplicative identity. So again, identity, you can do it, number stays the same. All right, last page. Okay, so opposites, reciprocals, and absolute values. So we're just gonna take this, we're gonna say what the opposite is and what the reciprocal is. I would go ahead right now and do this chart on your own. Pause the video, fill it out, double check your answers with mine, but I will go through them. So 24, the opposite of 24 would be -24. The reciprocal of it would be 1/24. Okay, this one's a mixed number. The easiest way to handle this for the reciprocal is to make it into a improper fraction. So hopefully you guys remember how to do improper fractions. You do the number on the outside times the denominator and you add the top. So we're going to do 5 times 3 is 15 plus 2 is 17. So your numerator is 17, denominator remains the same. All right, so the opposite of this is just putting a negative in front. So -5 2/3. The reciprocal, though, is taking the fraction and flipping it. So that's why we had to change it to an improper, because this is 3/17. Next one, we have -0.01. I would start by writing this as a fraction. So this would be negative. And then we're going to get 1 over, sorry, I put that equal sign a little bit close, but whatever. This is the 10th spot, this is the 100th spot. So it's 1 over, and then it's in the 100th spot. So this is -1/100th. All right, so the opposite would just be a positive 1/100th. So 0.01 positive. And then my reciprocal, that's why we did that fraction, would be -100. Just a mistake I see. Reciprocals keep the same sign as the number. Opposites are the ones that have the opposite sign. All right, √2. So the opposite of √2 would be -√2. The reciprocal would now be 1 over root 2. Please, please, please do not leave that like that. We don't leave that because that has a radical in the denominator. You have to rationalize it. So to rationalize the denominator, we have to multiply the numerator and the denominator by root 2. So let's go ahead and do that. And then this is going to equal, remember, we multiply straight across the top, straight across the bottom. So I do 1 times root 2, which gives me root 2. And then we have root 2 times root 2, or in other words, that's root 2 squared. So the radical and the squared cancel, or you can multiply the 2 times 2 is 4, so this is square root of 4. Square root of 4 is 2. There's no longer a radical in my denominator, so it is rationalized and good to go. All right, last little bit. Simplify each expression. So the absolute value of 9.2 would just be 9.2. Okay, this one you guys need to be careful about. So like absolute value signs are kind of like brackets or parentheses. Like you must do that first. You must do the inside and handle that first. So this one would go 0.4. The absolute value of negative 2.3 would be positive 2.3. So my answer is going to be a negative, and that would give me 0.92. All right, so again, simplify the inside of this absolute values. So this would give me absolute value of negative 5, and then keep simplifying. Absolute value of negative 5 would give me a 5. Do what's inside first. So this is a 7 minus, that is outside of the absolute value, so just leave it. Absolute value of 12 is 12, so this is 7 minus 12, which equals negative 5. And that would be our notes for 1.1.